About perpendicular bisectors of a triangle, and that they're concurrent, and that the point of concurrency is called the circumcenter, and that circumcenter is equidistant from the vertices of the triangle, and we could circumscribe the triangle from there. We talked about angle bisectors and the fact that they are concurrent, and that point of concurrency is called the incenter, and it's always inside the triangle, right? And remember, it was equidistant from the sides of the triangle, so we could inscribe the circle, right? Now we're going to talk about medians of a triangle. Medians go from the vertex to the midpoint. Now that's different than a perpendicular bisector, isn't it? Perpendicular bisector goes through the midpoint, but it's perpendicular to this side like this. A median isn't necessarily perpendicular. It goes from the vertex to the midpoint, okay? So it looks more like that. Now you find it the same way. Oh, dang, I should have said, good news, everybody. But I only say that when it's bad news, don't I? Yeah. So good news, everybody. We find the medians the same way we do perpendicular bisectors. We just make these arcs. And if you notice that if you do the same arc from all 3 points and just make them big, you can see all 3 intersections. Have anybody noticed that yet? So I can go there, and then I can come over here, and I can do this same thing. I didn't quite get that one far enough. But if I make all 3 of those arcs nice and big like that, let me move it up a little bit, I can actually see all 3 perpendicular bisectors. So if I wanted to draw those, I could come here like this, okay, and I could draw the perpendicular bisector. But now we're just concerned with medians, okay? So really, I just want to find the midpoint of that side of the triangle, and then I want to draw in the segment that goes from the vertex to the midpoint, like that. So that's a median. And I'm just going to do that again. We'll do that over here. So I find the midpoint, and then I go from the midpoint to the vertex like that. Now, when I find this midpoint and I draw the line from the midpoint to the vertex, and it's concurrent with the other 2, are you going to be shocked? I still think it's amazing. Still think that it's amazing. Uh-oh. Too long. Have to do a little bit of eyeballing, but I think that's pretty close. Concurrent. Okay? This point, since they're concurrent, guess what? It has a name. So far we've learned the circumcenter, the point of concurrency for the perpendicular bisectors. We have learned the incenter, the point of concurrency for the angle bisectors. And now this one is called the centroid. Yeah, like that. Centroid. The point of concurrence. Are you guys writing this down?
No.
Yes.
This is a stupid question.
No, it's not a stupid question. Go ahead.
It probably is. Whenever you would find the, I don't remember what the line
The perpendicular bisectors?
Yeah, when you were doing that, it would split the triangle into 3 triangles, and one of the triangles looked like it was isosceles all 3 times that you did it. Is it actually isosceles, or does it just look like this? Does that make sense?
I have never noticed that before, but next time we do one, we'll look. All right. Because if it is, I bet we can prove that it is. Okay. Medians. Concurrent. Centroid. Know how to draw them? Didn't have to learn anything new, did you? All you had to learn was what the median was rather than a perpendicular bisector. Okay, now what is the dealio with the centroid? It is not equidistant from the vertices of the triangle. You cannot circumscribe the triangle from that point. It is not equidistant from the sides of the triangle. You can see it's further here from that side than it is from this side. So we can't inscribe a circle, okay? But it does have a really cool thing going on. And so let me just point out the two pieces of the centroid. See that piece right there? And this piece up here. Okay? This piece right here is exactly half as long as that piece up there. It divides the median into a 1/3, 2/3 relationship. So let me give you an example. If this is 6 units long from A to M right there, then from M over here to point D is how long? It's 3 units long. And that happens all the time. Every single time we draw the median, okay, we draw the medians and we find the centroid, we get this 1/3, 2/3 relationship. Now, you might look at it like a 1/2 to 1/2 relationship because this is half as long here, right? But do you notice that the short piece of the median is 1/3 of the entire length? So MD, the measure of that segment, it is, what does this mean? It's equal to 1/3 of, what do I mean by of? Multiply of the whole thing, AD, the measure of AD. So that short piece is, it is 1/3 of the whole thing. And the longer piece, AM, what is it? It's got to be 2/3 of AD, of the measure of AD. So if you know the entire length, you can find each piece. If you know one of the two pieces, you can find the entire piece and the whole thing. So maybe we'll come over here and we'll say, well, this little one, let's say this whole thing this time, BE. So if I tell you the measure of BE is 6 units long, can you tell me the length of BM and ME? Yeah, this part's 4 and this part's 2. And you can just say to yourself, look, BM is 2/3 of the whole thing. See, that's an equation we can solve, isn't it? 2/3 of 6 is 4. 1/3 of 6 is 2, right? Okay? So there you go. That's how the centroid works. Kind of a cool deal. Okay? So the theorem says the centroid of a triangle is 2/3 of the distance from each vortex to the midpoint of the opposite side, which I'm sure made no sense to you whatsoever, but now that I explained it, you okay with that? So if I give you one of those 2 pieces or 3 pieces, you should be able to find the other 3. Let's look over on page 321 for a minute. Finding a centroid when you have the graph in a coordinate plane. So if I give you a triangle, you guys all see the blue triangle in the coordinate plane. Finding these medians. You can do that pretty easily in the coordinate plane without having to do the construction stuff, because you can find the midpoint of the opposite sides. Like look at RT. See that segment, everybody? B is the midpoint, isn't it? Are we sure? Yeah, because 2 plus 8 is 10, divided by 2 is 5. There's our x coordinate midpoint. And 1 plus 3 is 4, divided by 2 is 2. There's the y coordinates midpoint. We can see the midpoint. and we can draw in the median, can't we? Okay. Can we find the midpoint of ST?
Yeah.
What is the midpoint of ST? Oh, that's a bad one. 5 plus 8? 13 divided by 2? 6.5. And then 8 plus 3 is 11 divided by 2, 5.5. So 6.5, 5.5. We can still do that, can't we? Sure. You can mark that on the graph, and then you could draw that other median. There you go. I think you got that. You're fine with that part. Okay. Down to monitoring progress. There are 3 paths through a triangular park. Each path goes from the midpoint of one edge to the opposite corner. So what are those things called? What are they called? Medians. Okay. That point P right there has a name. What is its name? The centroid. And if you know the length of any of them, can you find the length of the other pieces, right? So PS, let's see, SC. Can you all find SC? 2,100 feet. Ooh, that's a big park. 2,100 feet for the measure of SC. Do you guys notice when I write the measure of the segment, I don't put the little line above it, do I? So if I just write it this way, I'm talking about the measure of the segment, not the segment itself. So that's 2,100 feet. PS is what fraction of that? Okay, it's 1/3 of the 2,100 feet. If you can say it, oh, well, that's 1/3 of it, well, then you just said the equation, didn't you? Okay, and of course, PC is 2/3 of the entire segment. And so what is this, 700, and this one's 1,400? You guys already knew that, didn't you? Okay, now for a little more interesting bit. Altitudes of triangles. Altitudes, ooh. What do you think about altitudes? What do you think the odds are they're concurrent? Who says yes? Concurrent? Who just realized Mr. Collard asked you a question you don't know what it is? All right, okay. So, altitudes of a triangle. Think about an altitude. An altitude goes from the vertex to a point that is perpendicular to this opposite side. Okay? So, it's we're kind of mixing everything together, and it's going to get confusing here, isn't it? Because we've got perpendicular bisectors. They're just perpendicular to that side, right? And they go through the midpoint. We have medians now. They go from the vertex to the midpoint. Now we have altitudes. They go through the vertex and they're perpendicular to this opposite side, but they don't necessarily go through the midpoint. Confused yet? All right, so we have to be able to do this. We have to be able to have a point that is not on a line and some line that the point's not on. And you have to be able to construct a line that goes through this point and is perpendicular to this line. This is the construction we have to do. I saw your eyes roll back in your head. You should have seen that. They went completely white that time. She's like, no. Okay, we can do this. Ready? We've done it before. Who remembers doing it before? Some of you? Okay, it's easy. Look. You put your compass here on this point, and you make a smiley face through your line. Got that? Okay. Then you come down at the 2 intersections of the smiley face, and you take your compass and you make an arc. Now, at this point, you can adjust your compass out, a little bit. Can you see it? Okay. Yeah, there we go. Okay, so I'm just gonna make an arc down here, and I'm gonna make that same arc from the other intersection like that. And then when I go through this point to that intersection, right there, that will be perpendicular. It'll go through this point and it will be perpendicular to this line. Now that's what we're going to use to find the altitudes of a triangle. So let's say this were a triangle. Okay? That's what we have to do in order to draw the altitude of a triangle. But I want you to notice something. See how this intersection isn't even on that part of the triangle? So you're given this triangle and you're supposed to find the altitude, but you might have to extend the sides of the triangle out to make that work. Okay? Let's try another side. Here, I'll do this one in red. So I'm going to go through this point, and I want it to be perpendicular to this side. So can you kind of see where it's going to hit? Kind of look like that, won't it? Okay. Well, when I go to make my smiley face, can you see how I don't have any intersection out here, do I? But what can I do? We can just extend that side of the triangle out. Now I can see it, can't I? And then I can come over from this intersection and from this intersection, and we can make an arc, make that same arc. So from there to our vertice. Okay, what do you think about that? That look like an altitude? It does, doesn't it? What about our third altitude? I've already shown you they are concurrent, right? Do we need to necessarily construct the third altitude, or do we know where it is? Very good. Okay, so that third one, we can come from here. As long as we go through that point of concurrency, there it is. There's the point of concurrency for the altitudes. Guess what? It has a name that you're probably going to have to remember, right? Orthocenter. That's right. Here's the thing about the orthocenter. It's the orthocenter. It's not equidistant from the vertices. It's not equidistant from the sides of the triangle. It's not, what was the deal with the median? Where the median intersected? Yeah, no 1/3, 2/3 relationship going on. It's just the orthocenter. That's it. Oh, you're making the orthocenter feel bad. What is the point of it? We actually use that quite a bit. So, what would we use it for? Yeah, because we're not going to circumscribe the circle. We're not going to inscribe. It's no 2/3, 1/3 relationship. Oh, it's not the balance point. One of these four that we talked about is actually the balance point of the triangle. So, if you put a pin on that point right there, you could balance the triangle on your pencil, or if you drill the hole through that point and then put a shaft through it and spun it, that would be the balance point. So even though the triangle isn't a regular triangle, you could still spin it around a shaft and it wouldn't wobble, because all your weight and everything would be evenly distributed as it went around, which is actually kind of a cool thing. No, the poor orthocenter. It's just the orthocenter.
Were you talking about the centroid?
Maybe. You might be able to construct it, cut it out, and see if it balances. What do you think? We might take some time to do that. But today, if you look on page 323, you'll see a really good summary of all of this. The type of line, what it does, what it looks like. And I like that they just draw one of them in each triangle so you can see what's going on. The point of concurrency's name, the property you have to know, and then an example of that. To prepare for the test, I would have all of that drawn out yourself. I would have an example of that. I would make sure that as part of my example, that I've got the construction done so that I can remember how to do that on the test and all that kind of good stuff. What's that? Oh. Okay. Here you go. Chapter 6.3.